This is Donna Nelson at the University of Oklahoma, filming one of my lectures for my organic chemistry class. And so today we will continue with alpha carbon chemistry, enols and enolates, using chapter 21 out of David Klein's organic chemistry textbook. So, to begin, this chapter is going to have 4 different filmed lectures, and here we are, starting on the first one today, Introduction to Alpha Carbon Chemistry, Enols and Enolates. So, the Greek letters are used to describe the proximity of carbon atoms relative to the carbonyl group. So, if a carbon is directly attached to the carbon of the carbonyl, it's in the alpha position. One farther position away would be in the beta position, and then gamma position, then delta position, and you simply keep going farther out. The chapter will primarily explore reactions that take place at the alpha carbon. So the alpha carbon position is the one that's important this time. So alpha protons, the ones that are directly attached to the carbonyl carbon. And so if you have a substituent directly attached, so for example, if this were a proton, you would say that it's a proton at the alpha position, or you might have a halogen, so it would be a halogen at the alpha position. So this is called the alpha position as well. And there may be other designators, other language that I'll use during this chapter, and so you'll just have to note there are certain terms that are used to describe this position, or the alpha carbon, or an alpha proton, meaning a proton that is attached to the alpha carbon. So here you can see that the carbonyl is in equilibrium with the enol, so this is the keto form and the enol form of the carbonyl. And you can see that the double bond has just simply migrated. So here you have a carbon-carbon double bond and a hydroxyl group instead of a carbonyl, a carbon-oxygen double bond. Now notice these are not resonance structures. This is an equilibrium. Remember that in resonance structures, only electrons move, and here you obviously have a proton moving. So these are not resonance structures. These are equilibrium structures, and they are tautomers. These are called tautomers, special types of equilibrium structures. And so here you can have the reaction to have substitution take place at the alpha position, which is what we're going to see mostly in this chapter. And you can see that here it is taking place. This route is through an acidic route. This route is through a basic route. So here you can see the negative charge where a proton has been removed, and then a substituent is attached at the alpha position. Here it can still take place, but you have no basic conditions. So this is going to be under acidic or neutral conditions. So here this is the enol, and this is the enolate. This is the neutral form, and this is the anionic form. So most of the substitution reactions that we're going to cover, where we have introduced a substituent at the alpha position, we'll go through either the enol or the enolate. Enol if it's under acidic or neutral conditions, the enolate if it's under basic conditions. In the presence of an acid or base, a ketone or aldehyde exists in equilibrium. So this is the equilibrium. This is the keto. and enol form of the carbonyl. These are tautomers of each other. The equilibrium does generally favor the keto form, the ketone. Even if this were an aldehyde, it would still be called the keto form of the aldehyde. So, and this is the enol form. And so you can see that this is vastly preferred to have the carbonyl instead of the alcohol functionality. But that's not always true. You're going to see a couple of examples. So here's an exception. This is a 1,3-diketone, and it doesn't matter what substituents are on either side. So this is, here you can see that this is the enol form of this carbonyl. And so you have one keto form and one enol form, and this is stabilized by conjugation right here among these 4 atoms. And also, you can see that there's opportunity for hydrogen bonding. So remember that cyclohexane, which is a 6-membered ring, is especially stable because of the bond angles. And so similarly here, anytime that you see a 6-membered ring possible, that is going to be stable because even though you have free rotation about single bonds, it turns out that these atoms just sort of, as they're flopping around, they will flop into, when they get to a 6-membered ring, that's sort of stable because and especially allowed because the bond angles are just right. So here you can see that you have the possibility of hydrogen bonding, and so the hydrogen bonding also stabilizes this enol form, the enol form over here. And so this is one of the exceptions. So this exists in 70 to 90%, 10% to 30%, depending upon what the substituents are, of course. And so remember, this is an equilibrium. So these are keto-enol forms, tautomers of this molecule. Another example where you have an enol form is favored is in phenol. So you will see that this is the enol form and this is the keto form. And so this is an enol with aromatic stability. Here the aromaticity is lost, and so this the equilibrium is pushed greatly to the right, and this molecule is vastly favored because of the aromaticity that is provided by this enol form, the enol structure. Now let's look at the actual mechanism of this conversion. Remember, these are not resonance structures. They are equilibrium forms, and so there has to be a mechanistic pathway in which one can be obtained from the other. So we're going to have 2 different pathways, one under acidic conditions and the other one is under basic conditions. So first let's look at the acidic conditions, even though it's a little bit harder because it has more steps. So remember that the first step in the vast majority of organic chemistry reactions, when it's under acidic conditions, the first step is going to be protonation of a functional group. And so here, the only functional group that you have is the carbonyl. that is going to become protonated under these acidic conditions. And so you have a pair of electrons plucking off a proton off of the hydronium molecule, and the pair of electrons in the OH bond moving back onto oxygen to satisfy this positive charge. And so now the carbonyl is bearing the positive charge, and you do have a resonance structure here, because the difference between these two structures is only electrons are moving. So this is indeed a resonance structure. The pair of electrons in the pi bond is moving on to oxygen to satisfy the positive charge. So now you have two lone pairs on oxygen, and the positive charge has moved down onto carbon because that carbon is electron deficient. It's only surrounded by 6 electrons now, 3 pairs. And so then this is still a cation, and you're trying to get the neutral molecule, so obviously this molecule is going to have to lose a proton. So the water picks up a proton, a pair of electrons on oxygen, forms a bond to hydrogen, so you have the OH bond, so you have an OH bond formed here, and the pair of electrons in the carbon-hydrogen bond move back and form a pi bond, satisfying the positive charge on carbon. And so this becomes the hydronium ion. And so you can see that this is indeed functioning as a catalyst because it's regenerated. And so here now is the enol form of your carbonyl, the keto form and the enol form. So this is the way that it is obtained mechanistically. And in order to go back, I mean, obviously, this is a reversible reaction. You simply reverse the steps. And so here what would happen is, this pair of electrons would pick up a proton off of the hydronium ion in order to go back. So now, under basic conditions, it's a little bit easier. A few fewer arrows, and so this is under basic conditions. You're not going to see any plus charges under basic conditions. So here you have hydroxide, pluck a proton off of the keto form, and the pair of electrons, this has to be at the alpha position, the pair of electrons involved in the carbon-hydrogen bond move on to carbon, forming a negative charge. And you can see there are 2 resonance structures here, one having the negative charge on carbon, one having the negative charge on oxygen. And so these are 2 resonance structures. The pi bond also migrates. Here you have the carbon-oxygen pi bond. Here's the carbon-carbon pi bond. And so now the negative charge has moved out onto oxygen. And so this is an alkoxide. And so notice the resonance arrow. And so these are indeed resonance structures. Only electrons are moving. Now a pair of electrons on oxygen moves in to pluck a proton off of water, forming an oxygen-hydrogen bond, as you can see right over here. This satisfies the negative charge on oxygen, so now oxygen is neutral, but the pair of electrons moves back onto oxygen, and so you're going to have 3 pairs of electrons on this oxygen now, and it will bear a negative charge. So you can see that the base is indeed functioning as a catalyst, so it is regenerated. So now you have the enol formed. This is the keto form, enol form. And in order to, since it is an equilibrium, it goes in either direction. And so you would simply reverse the arrows to get back to the keto form. So you will always have some of the keto form and some of the enol form available. They are in equilibrium, even if it is 99.99% of one and 0.01% of the other. You will have some small amount, you will always have some small amount available to you in solution. That becomes important because even if only 0.01% of one of the forms exists, it still can be the form that a mechanism goes through. So in other words, you can have a vast preponderance of one form and still go through the other form in the mechanism. So it only has to be available for use in a mechanism. It does not have to be the major form, the major component. It only has to be available to proceed through in order to have a mechanism use it. And so this actually becomes much more important than might be realized. So here you can see the resonance structures, and so you can see that you have a large amount of electron density around oxygen, and so you can see here that is red and sort of red colored, indicating a large amount of electron density. And also here you can see this alpha carbon is going to have a large amount of electron density because it's electron rich. There's a negative charge there. So a strong base can deprotonate at that alpha position, generating the enolate. This is the enolate anion. There is just one enolate anion. These are two different resonance structures describing that enolate anion. The enolate anion will have a partial negative charge at oxygen and a partial negative charge at carbon, because remember, there is just one structure that is described by these two resonance forms. So the carbon is more nucleophilic here, much more than over here, because this is bearing a negative charge. So the enolate anion is much more reactive than the neutral enol, of course. And so you would expect that because an anion is going to be more reactive than a neutral molecule. So it can undergo, the enolate anion can undergo either oxygen attack, O attack, it's abbreviated, to attach an electrophile at oxygen, or it can undergo C attack, that is attack at carbon, to form a bond to the electrophile. And either of those can be observed, but usually you're going to have C attack. Although this is known, this does happen, it can happen, and in some cases it is the preferred attack given a particular electrophile. But in the vast majority of cases, you're going to have C attack, attack at carbon. So it depends on where you have drawn the negative charge. This is usually what you will see drawn, because the enolate anion will be more stable to have oxygen on the negative charge. And so it's usually drawn in this structure. It's usually drawn this way with the negative charge on oxygen simply because oxygen is more electronegative than carbon, and it bears the negative charge better more easily than the carbon. But actually these are just two different resonance structures. Nevertheless, you usually see this drawn with the negative charge on oxygen. And so here, to show the attack on the electrophile, the pair of electrons moves in, forms the double bond, the carbon-oxygen pi bond, and the pair of electrons in this pi bond move out to form this Ce bond. And so notice you have an anion reacting with a cation, so now you have a neutral molecule. So this would be a very rapid reaction. Once again, you have, in this example, you have an anion reacting with a cation, and this is actually leading to the same product. Here, it's simply a matter of how it's drawn. If you start out with the negative charge drawn on carbon, then you simply just include only the right-hand arrow. So that's all that's included here. But the arrow is coming from the lone pair instead of the pi bond. So here you just have one arrow, whereas over here you need two. So here you are forming a bond between carbon and the electrophile. But usually this is what you will see drawn, even though it requires a little extra work because you're drawing another arrow, and this is the reason that you see this more often is because the negative charge is more stable on oxygen. And even though they both lead to the same product. So in this chapter, you're going to see a lot of these reactions. Mostly this one. So now we've talked about the alpha position, beta position, gamma position. What you're going to see is that the alpha protons are the only ones that are acidic. Okay, this makes sense because if you remove one of these protons, you're going to generate a negative charge, and then you're going to have different resonance structures. If a beta or gamma proton is removed, there's no relationship between the beta or gamma position to the carbonyl, no way to stabilize that, and so the alpha protons are the only ones that are acidic because of their close proximity to the carbonyl. The pKa values of the alpha protons must be considered when choosing the base that is used to form them. So here you're going, in a reaction, you will need a base to remove this proton from the alpha position, or from this alpha position, or from this alpha position. And depending on the enolate anion that is obtained, you can see the difference in these enolate anions is what the substituent, the other substituent that is attached to the carbonyl carbon. So here you have a methyl, here you have a phenyl, here you have just a hydrogen. And so in each case, you have an enolate here. You can see the arrows that are drawn that describes the two resonance structures. Okay, and notice the resonance arrows. So these are indeed two resonance structures, only electrons have moved. So you can see the negative charge residing on carbon, then the negative charge residing on oxygen. So the only thing that is different in these is the substituent that is attached to the carbonyl carbon. So this is showing you a trend. And so obviously you can see that here, you have a pKa of 19.2, and then a pKa of 18.3, pKa of 16.7. So the acetaldehyde is most acidic. more acidic than acetophenone, where you have the benzene ring, and more acidic than acetone. So what trend is going on here? Well, it depends on how, relative to hydrogen, how much electron donation is going on, because here you have no electron donation going on at all, and you know that relative to hydrogen, carbon is more electron donating or electron releasing than hydrogen. So here you have carbon, carbon, and so you will expect these, since they are electron releasing, here electron releasing, and this is the anionic portion of the molecule, and if they are electron releasing, these will destabilize the anion if these are electron releasing into the anionic part of the molecule. And so if this is electron releasing, there will be a tendency to destabilize the anion and stay with the neutral molecule with the proton attached. So here you have, relative to hydrogen, carbon is more electron releasing, carbon is more electron releasing. And so that explains why these anions are a little less stable, and so these parent molecules will be a little less acidic. Now, relative to each other, these two, which both have carbon attached to the carbonyl, this is a methyl, and this is phenyl, so that's an sp2 hybridized carbon and an sp3 hybridized carbon. And so sp2 hybridized carbons are a little less electron donating, and so that is reflected here in a little bit higher acidity for acetophenone than acetone. When pKa values of the base and the enolate are similar, both products and reactants are present in significant amounts. And so here you can see the ethoxide is flicking off a proton. This has a pKa of 16.7. The ethanol has a pKa of 15.9. And so this one is going to be a little bit more acidic, and you can see that it is predicted to exist as ethoxide and the aldehyde. Oops. So, but in order to irreversibly form the enolate, you can use something like sodium hydride here. So the sodium cation is not shown, but if H minus plucks off H plus, the hydrogen gas will be evolved. It will be removed from the solution as soon as it's formed, and you will be left with this enolate and sodium counter ion, sodium cation as the counter ion. Another way is to use lithium diisopropyl amide, and so you can see the way that this is generated is to use N-butyl lithium. It will pluck a proton off of the diisopropyl amine, leaving you with the lithium diisopropyl amide and butane from the butyl lithium. So this is another way to form a very strong base. So this gives you two ways to generate the enolate, so that you will have mostly the enolate in the solution. So when the LDA, the lithium diisopropyl amide, is used to form the enolate, it's no longer drawn as an equilibrium. This is so much more basic than the enolate that it simply pulls off a proton, pair of electrons moves back onto carbon. You have the enolate, and you have this amine, which is really not acidic at all. It has a pKa of 36. This is a very strong base. It flux off a proton. It will not attack at the carbonyl because it's not a good nucleophile. It's sterically blocked from being a nucleophile, so you don't have to worry about attack at the carbonyl. When the protons, as in here, are alpha to 2 carbonyl groups, they are much more acidic. Here, so this has a pKa of 9. This has a pKa of 16.7. Notice the proton is alpha to only 1 carbonyl. And the reason for that is that the negative charge that is generated at this carbon, when one of those protons is removed, you still have 1 proton left here. So 1 proton is removed, it forms a negative charge, and there are more resonance structures here. So this anion is more resonance stabilized. This enolate is more stabilized because it has more resonance structures than simply the enolate that would come from this carbonyl, this acetaldehyde. The 1,3-dicarbonyls are acidic enough to be irreversibly deprotonated simply using ethoxide. And remember, that was not possible with just something like acetaldehyde. So here, when ethoxide removes this proton, you generate this highly stabilized enolate simply using this base, which is a little bit milder than than LDA or sodium hydride. And here you have ethanol formed, which is much less acidic than this 1,3-dicarbonyl. So here is sort of a summary. If you have just a ketone as opposed to a 1,3-dicarbonyl compound, if you have a ketone and you use sodium ethoxide, you will have both the enolate and the ketone present at equilibrium. If you use sodium hydride or LDA, you will have, so this will be an equilibrium, this one is not. This is an irreversible enolate formation. Okay, so here you have some of the enolate and some of the reactant. Here you do not have any of the reactant. But if you go to the 1,3-dicarbonyl and you use sodium ethoxide, you will have almost complete enolate formation. As it says here, lithium diisopropyl amide is not necessary. However, if, let's say, that you happen to have this on hand, or this was being run in the presence of another reaction and you wanted to do, hit 2 functionalities at once, this would still react. So these two would do the same thing, but they're not necessary. So you can simply use sodium ethoxide, and you usually want to use the mildest reagent possible, just for reasons such as expense and safety and disposal, etc. So this takes care of section 21.1, enolate formation. So in the next lecture, we will go on using those enolates.